Hello, guys, and welcome back to Count to 10 and a very happy new year. My name is Ani, and today we have a very special guest joining me. Now, I know I always say this whenever we have a guest, but today joining me is Dr. Anthony Haid, who's a current primary examiner. I'm really excited to have Anthony on today, and he's going to be volunteering some of his time to talk about a topic that is really core knowledge, and that is propofol pharmacokinetics and looking at the TCI model. This is going to be a very in-depth conversation that starts off with some basic fundamental equations and then works into the harder stuff, looking at applications with the Marsh, Schneider, and a little bit about the Eleveld model right at the end. Now, I definitely recommend that this podcast requires some prerequisite knowledge and some basic understanding of general pharmacology to get the best bang for buck. However, this is a podcast that you can come back to in the future when you have some basic knowledge and the fundamentals, and then really see what your understanding's like. This is normally a talk that Anthony gives at the primary exam course, and it's best given in a face-to-face medium. But Anthony has done a lot of work behind the scenes to adapt his talk to the podcast format, and I really want to thank him for that. I'm really excited for you guys to listen to this episode, and at the end, we give a little shout out to Anthony and his band, The Volatiles. I'll put one of their songs at the end, which I hope you'll enjoy. It's very catchy. And with that said, let's dive straight into today's talk.
1, 2, 3, 4.
Hey Anthony, thank you for joining me and thank you for volunteering some time on your weekend. I'm really excited to be talking about this topic with you, which is pharmacokinetics, looking at the TCI model. And we're going to be using propofol as an example. Why this topic before we get started?
Well, I think this topic is easy to understand for some minority of people who read the textbooks and understand all the mathematics, and it can cause misunderstanding for people who don't have a good understanding and they just don't speak that language. So I've been teaching this topic for, I guess, 5 or 10 years, and I've developed a way of explaining it and a way of understanding it that doesn't rely heavily on mathematics. It's not an exact understanding, but it's close enough to get you by, and it's close enough to kind of make it so that you can understand how to use each of the different common propofol TCI models that you encounter in everyday clinical practice.
Awesome. And I know that you've done a lot of work to make this talk that you normally give at the primary exam course into a palatable kind of platform so that people who are listening on the podcast can understand it. So I really appreciate that. Before we get started, is there any conflicts of interest that you want to disclose? Because I know that you are a primary examiner, but I don't think you're talking about anything that's related specifically that's going to jeopardize your role as a primary examiner.
Yes, so I do lecture at the primary exam official course, and I have taught on this. All of the content here predates my involvement in the exam, but I am also a current primary examiner for the college. Whenever I say that when I'm at a course, people then interpret everything I say as this is the magic phrase that I need to say or write in an exam in order to get the mark. There is no magic phrases that I'm going to say today. What I'm trying to impart is my understanding of how to distill a complex topic down into a simplified way of being able to explain it. Because if you can explain it in a written or a verbal format, then you understand it. And if you understand it, you can answer any exam content question on the exam that you might get asked.
Yeah, awesome. And I must say, I'm one of the few that was actually guilty of this whenever you got some piece of advice from an exam and you're like, that's verbatim. I must remember that and use that in the exam. So I think just understanding the basic facts and then your ability to understand and explain in the actual exam is more important than recalling facts, because you as an examiner will be able to see through that very clearly.
Yes, fortunately or unfortunately, depending on your frame, depending on the way you look at it. And so I do like to use examples and numbers, specific numbers, but I'm using them to illustrate a topic. You don't need to remember numbers. You can answer questions by using qualitative terms like X is greater than Y, therefore the following things happen. But if you know that X is twice as high as Y, it helps solidify these abstract concepts and make them more concrete. So that's the reason why I'm going to be using actual numbers in my explanations.
Yeah. And for people that are listening, we're also going to be giving some prompts and going through some real-time examples. And you can follow us either at work, if you listen to this podcast, by using a syringe and chucking it into your TIVA model and then putting in the numbers that we talk about. Or we also have this app or website that we're going to be using called simtiva.app. And you can use the same examples that we're talking about or different examples to then solidify your knowledge and understanding of the concepts that Anthony will be going through today. So throughout this episode, we'll be giving prompts on when you can use that. And hopefully you'll be able to listen back to this in your own time and then use it just to solidify what you're going to be learning today. So saying that, let's get started. And I'm going to just share the initial slides.
Yeah, so there's a few equations that you do need to know when you're talking about this topic. And I've boiled it down to 6 equations. The first 4 equations I want to go through now, because they pertain to the plasma concentration versus time curve when you're giving a bolus dose. And then equation 5 and 6 are a little bit more complicated. So the first equation you have to think about pertains to when you are giving a bolus dose of propofol. Now, when you're giving propofol with the aim of maintaining with a volatile like sevoflurane, typically the way people think about that is they think, oh, well, I'm going to give this person about 200 milligrams or 100 milligrams, and you're going to base that calculation based on what the standard dose is, and then you might adjust it up or adjust it down based on a variety of different factors. The way a pump works is you tell the pump, I want the target concentration to be 5, and then it calculates the bolus dose based on the volume distribution of the central compartment if you're doing plasma targeting. So the first equation you need to understand is that the bolus dose of propofol in milligrams divided by the V1 in litres is equal to your initial plasma concentration in micrograms per mil. Micrograms per mil is exactly the same as milligrams per litre. So you can see how dividing milligrams by litre gives you a concentration. And the simplest way to think about this is plasma concentration targeting. So the simplest way to think about it is the Marsh model targeting a plasma concentration of, let's say, 5 micrograms per mil. So after you've given your bolus dose, what typically happens is that the drug is cleared from the plasma, and the rate at which it is cleared, it's first order kinetics. So the second equation is the equation for clearance. Now, clearance is in the units of litres per minute, and clearance is equal to your rate constant multiplied by your V1. V1 is the same V1 we used in equation 1. It's measured in litres, and your rate constant has the units of minutes raised to the -1. And you can see how if you multiply V1 in litres by K, which is minutes to the -1, you end up with the units of litres per minute. And litres per minute is what the units are for clearance. So that's the clearance equation. Now, the difficulty in propofol pharmacokinetics is you have elimination clearance, where propofol is cleared from the plasma, and then you have intercompartmental clearance, where propofol is cleared from V1 to V2 or from V1 to V3. But the fundamental clearance equation is the same, and the rate constant is the key to how quickly or how slowly the propofol is cleared. So if you take your initial plasma concentration and then you factor in that it is going to be cleared from the plasma, what you end up with is a plasma concentration versus time curve. And the next thing that you need to know is the equation number 3. If your initial concentration is C0, or let's say 5 micrograms per mil, and you want to estimate what your concentration is going to be at a particular time, that is C subscript T, concentration at any given point in time. So the concentration at any given point in time, measured in micrograms per mil, is equal to your initial concentration, which is C0, micrograms per mil, multiplied by a number. And that number is e to the -kt. This is difficult to understand, but it's essentially just the standard mathematical equation for a negative exponential washout function. We have 2 negative exponential functions in anesthesia. There's a negative exponential wash-in function, which is, for example, your FA-FI curve in volatile anesthesia. And then you have a negative exponential washout curve, which is the plasma concentration decaying over time. And all a negative exponential function is different to a linear function in that the rate of change changes with time compared to a straight line where the rate of change is constant. And negative exponential simply means that the rate of change decreases over time. So if you look at that little thing that you're multiplying initial concentration by? It's E raised to the negative KT. E is simply a number, kind of like pi. Negative means the rate of change decreases with time. T is the time that you're trying to figure out what the plasma concentration is at, and K is the rate constant once again. Now, rate constants are difficult to understand for a lot of people because they have the units of minutes raised to the -1, and they're kind of confusing. All the rate constant is, the best way to think about it is that it is a number between 0 and 1, and it describes how quickly a negative exponential function occurs. So if it makes it easier for you to understand, you can think about it in forms of the next equation. The next equation, equation number 4, is the equation that relates half-time to rate constant. So a half-time is easier for a lot of people to understand. It's measured in minutes. So if you have a plasma concentration of 5, and then after 5 minutes it drops to 2.5, the half-time of that function is 5 minutes. So the equation is half-time measured in minutes is equal to 0.693 divided by your rate constant, which is measured in minutes to the -1. And so the qualitative rule of thumb is the higher your value for K, the faster the process happens and the shorter your half-time. Conversely, the lower your rate constant, the closer it is to 0, the slower a process occurs and the longer your half-time. So if you have 3 simultaneous exponential negative exponential washout curves happening with 3 separate rate constants, you're going to have 3 separate processes with a short half-time, an intermediate half-time, and a long half-time. And so that's what's actually happening when we do a 3-compartment model. So those 4 equations will help you, and I might go through how they apply to the plasma concentration time curve first before we go back and talk about the other 2 equations, if that's okay.
Yeah.
So if you just imagine in your mind a standard plasma concentration versus time curve, and so for those playing at home, the best curve to look at is the one from Miller's. So if you look at the latest edition of Miller's 10th edition, figure 21.2, you can see exactly what we're looking at. But basically what you're looking at is, well, Arnie, do you want to just describe what's on the screen maybe? And I'll...
Yeah. So everything that Anthony's talking about is from the Miller's Anesthesia 10th edition, like he said. And what we're seeing here is on the y-axis, you have the classic plasma concentration in mics per mil. And on the x-axis, you have time, and whether that's time in minutes, seconds, whatever. But in this context, it's time in minutes. What we have initially when we're using Propofol example is this classic rapid increase in plasma concentration as the blood goes into the V1 compartment. So you get this massive linear increase straight away, which reaches its peak very quickly, and that's called the peak plasma concentration. From that point, you then get the exponential decline in this curve. And when we talk about the 3-compartmental model, we can then talk about this as a tri-exponential decline. But for the basis of just talking right now, we just have an exponential decline with time. And within this exponential decline with time, our drug is having its desired effect within its therapeutic range somewhere between 1.5 minutes to 4 to 5 minutes. And as we get closer to 7 to 8 minutes, this is just with a single bolus of Propofol, our drug drops out of where the therapeutic range is and the desired effect goes away, and the patient has a wake up from that Propofol bolus. So this is a very simple curve, and it can be applied to any bolus of a drug given in an IV form, because essentially it follows the same pattern of a linear increase, reaching its peak plasma concentration, and then following an exponential decline in the context of us talking about a 3-compartmental model.
Okay, that's a pretty good jumping off point. So I want to go through and talk about how each of the equations pertain to this curve. So equation number 1 is that if you give a bolus in milligrams and you divide it by a V1, it equals an initial plasma concentration, all right? Now, the complicated thing here is when you run imagine you're running an experiment and you're giving a bolus dose. It's pretty easy to know the exact milligrams that you're giving. And in this experiment, you're measuring the plasma concentration. That's a little bit more hard. We don't do it routinely in clinical practice, but you can imagine yourself in a research setting where you put in you either do a venous stab or you do an arterial cannula and you take blood off or whatever, and you would come up with like, well, we'll give the bolus and we'll take the blood from the arterial cannula, we'll take it 15 seconds after it's administered, and then we'll send it off to the lab, and they'll measure it, and they'll tell us the plasma concentration. The V1 is calculated from those two numbers. So V1 is kind of made up, if you like. It simply describes the relationship between the bolus that you administer and the initial peak plasma concentration that you observe. Now, the relationship is more important than the actual numbers. So if you look up different reference textbooks, you'll find different numbers for V1 that pertain to different mathematical pharmacokinetic models. So this is the problem with volume distribution, is the same term, volume distribution, can literally apply to a bunch of different things that you're talking about. You might be talking about VD as a concept. You might be talking about VD initial versus VD at time of peak effect versus VD at steady state. You might be talking about V1 as a concept. You might be talking about the actual V1 in a specific Marsh model versus Schneider model, okay? So whenever you look at V1, rather than think about it as a physical volume, think about it as simply the relationship between bolus and plasma concentration. To illustrate that, let's pretend you give someone 100 milligram bolus and you measure the plasma concentration in a set way. What would you expect to happen if you doubled the bolus and you gave them 200 milligrams as opposed to 100 milligrams, and you measured the plasma concentration in the exact same way? Well, what you should expect is the concentration will be roughly twice as high, because that's all the equation said. If you give half the bolus dose, let's say you give 50 milligrams instead of 100, and then you measure the plasma concentration in the same way, the plasma concentration will peak at about half what it was before. Now, the problem occurs if you start measuring the plasma concentration in a variety of different ways, right? If you measure it venous versus arterial, if you measure it after 15 seconds versus after 30 seconds, if you measure it in people who do not have exactly the same physiology, different body shapes, different age or sex or muscle composition, if you measure it in the same person, but their physiology has changed, obviously these changes are going to give you different numbers. So the best way to think about it is simply the relationship between bolus and plasma concentration is this thing that we call V1. That thing that we call V1 is not the same as the plasma concentration, okay? Now, once you've got that understood, then you can start playing around. And let's say you have two patients and you give them both 100 milligrams, exactly the same bolus. And let's say you measure the plasma concentration after the bolus, and one of them has a higher plasma concentration than the other. What you can infer from that is there is something different about that patient's physiology, and the way we express that is the V1 is smaller, okay? So milligrams divided by a smaller volume will give you a higher initial peak plasma concentration. And the most obvious clinical example for there is the extremes of age. Young children, 5-year-olds, have a very high volume distribution, which is why you give them a higher bolus, milligram per kilogram wise, and very old people have a low volume distribution, and that's one of the reasons, but not necessarily the only reason, why you have to reduce your bolus dose in the elderly person. Now, the second equation is the clearance equation. Clearance equals rate constant multiplied by V1. The K is the rate constant. It tells you how quickly that negative exponential washout curve occurs. So if your K is very, very high, it's a very, very fast washout, and it's going to be a very, very scalloped curve. So your peak is going to drop down very, very quickly, and it's going to be very scalloped out. If your K is very low, it's going to be a very, very gradual descent. So in other words, if you have a negative exponential washout curve with a high K, it's going to have a very short half time. And you can imagine in your mind what it would look like. If you have a very, very low K, it's going to have a long half time. And so you can change the shape of the curve by changing the K. If that's difficult for you to understand, anytime you see the word, the letter K for rate constant, in your mind, just think it's the opposite of half time. It's not literally the opposite, but if the K goes up, the half time goes down, and vice versa. And finally, if you have time on the x-axis and you know the value for your initial plasma concentration and you know the value for K, you can just mathematically solve for the equation to find the concentration at any given point in time. And so that's what your pump is doing, because your pump needs to know, once you put the bolus drug into the central compartment, that's the initial bolus, it then needs to calculate what is the rate of propofol administration that I need to administer in order to maintain the concentration at that level. So that's how those four equations pertain to this graph.
So then should we go back to the other two equations now?
Yeah, so why don't we go on to, because the fifth equation, we'll go back to the fifth equation, and that's that's a difficult equation though. So I'm going to show it to you. Then I want to illustrate with a three-compartment model, and then we're going to come back to it. So the equation is that the rate of propofol administration, now we think about in terms of mils per hour, but in this equation it's milligrams per minute. So once you get the milligrams per minute, you can multiply it by 60 and then divide it by 10, and that will be mils per hour, right? So the rate of administration is going to be equal to your initial bolus in milligrams multiplied by, and then open brackets, a whole bunch of complicated mathematics, close brackets. And what's inside those brackets is simply a rate constant, okay? So the rate constant is going to be the sum of all of the rate constants that make up your model. It's going to be the rate constant for elimination, the rate constants for distribution, and the rate constants for redistribution. And why don't we go through an example of what the Marsh model actually does, and then we'll come back and revisit this equation number 5.
Yep. Should we do it on the SimTiva app?
Yeah, well, why don't we go through what's actually happening? So what you've got on the screen now, I just want to describe what you've got on the screen there.
Everyone should know the three-compartmental model because it's very ingrained in our curriculum. But what it describes is this drug that we're giving, and it can be any drug, and for this purposes, we're talking about propofol, is administered into that V1, which is known as the central compartment. And from this central compartment, we have drugs going into 3 different areas. We have drugs going into V2, which is the rapidly equilibrating compartment. And what the rate constants just essentially are, explaining how fast a drug goes from V1 to V2, which is referred to as K12, or how fast a drug goes back from V2 into V1, which is referred to as K21. The same thing happens when we talk about V3, which is the slowly equilibrating compartment. So going from the central compartment, that would be the rate constant would be K13, and going back out from that compartment would be K31. Everything needs to go back into the central compartment to then be eliminated, and that elimination is then referred to as the elimination constant, which is referred to as K10. Drugs that go to the effect site, which is a separate thing, then also come from the central compartment. So from V1, they go to the effect site, and we'll go into talking about KEOs later on. But the basic understanding for this model is that the drug that we give goes into the central compartment, and it goes into 2 different areas, a rapidly equilibrating and a slow equilibrating compartments referred to as V2 and V3. We have constants that describe the movement of drug into those compartments and constants that describe the drug out of those compartments back into the central compartment. And then we have a constant that describes from the central compartment the elimination of the drug out of our body, which is referred to as the elimination constant, which is K10, which we'll refer to multiple times throughout this discussion.
Okay, that's a pretty good summary. So let's start with the simplest model, the Marsh model, targeting a plasma concentration of 5. Let's ignore the effect site, and let's just think about what that means. So one of the things that people get bogged down with is getting the propofol pharmacokinetic models mixed up with the volatile models. So the correct way to discuss this is you've got a V1 central compartment, a V2 rapidly equilibrating compartment, and a V3 slowly equilibrating compartment. You should not be conflating V1 with plasma volume and V2 with vessel-rich group and V3 with vessel-poor group. The pharmacokinetics of volatiles is a separate issue where you talk about vessel-rich group, muscle, vessel-poor group, bone, etc. So what I want you to do is pretend we've got an 88 kilo person who's 20 years old, they're 188 centimeters tall, and we want to target a plasma concentration of 5 in the central compartment. What is it that the actual thing does? So if we proceed,
and everyone who's listening can do this at home. So this is on the SimTiva app, SIMTIVA.app. You can put in these models, and we're going to just target plasma concentration. And we're going to say proceed here. And we're going to try to target a plasma concentration of 5.
Yeah.
And so when we start this, this will show what's going to happen in real time.
Correct. So what this does is not exactly the same, but it's an approximation for people who don't have Propofol TCI pumps. I think what this app is you plug in what you want to do, and then it tells you what bolus do you need to give, and then what's your initial rate in mils per hour, and when do you have to reduce the rate. So if you have a Marsh model, the age and the height and the sex are irrelevant. Marsh only changes parameters based on the weight that you input. Now, the reason I chose 88 kilograms as an input is because if you have an 88 kilogram input weight, it just so happens that the volume for V1 ends up being about 20 litres, and that makes the maths easy. So if you're calculating your bolus dose, think about the 20-litre central compartment as being a bucket, 20 litres high, right? And you want an input, you want to target your plasma concentration of 5 marbles per litre, okay? So if you want to get a concentration of 5 marbles per litre, you have to put 100 marbles into a 20-litre bucket. And that's exactly the same as putting 100 milligrams into a 20-litre V1. And that's exactly what it does. That's why the bolus dose is 100 milligrams. Now, if you scroll down in Simtiva and look at the model parameters, it has the Marsh model, and it has a little reference for where you go to. It's got VC equals 20. It's not exactly 20. It's 20.064. VC scales up or down depending on your input weight. Okay, so the rate constants in the Marsh model do not change at all. The only thing that changes is the volume of distribution of the central compartment. Now, the volumes of distribution of V2 and V3 also change, but they are simply a mathematical derivative of the V1. So here's a little thought experiment. If your 88 kilo person has a V1 of 20 litres, what do you think the V1 would be if you halved the weight to 44 kilograms? You can do it yourself if you like, but it's essentially just linear. So that would give you a VC of 10 litres, and it means your initial bolus dose would be 50 milligrams. So let's just go back to the 3-compartment model, and I'll talk you through my marble in a bucket analogy, and we might come back to those rates later. So if you think in your mind about a 20-litre bucket and you've poured 100 marbles in, your concentration of marbles in the bucket is 5 marbles per litre. Now let's say that there are 3 simultaneously occurring negative exponential washout curves happening. And the rate at which the marbles are leaving the bucket through the 3 arrows is governed by the rate constants. Now, there's 3 rate constants that are relevant in the initial phase. K10 is the rate constant for elimination. And K10 is equal to 0.119 minutes to the negative 1. That's a difficult concept to understand, but all it means is about 11.9% of what's in V1 will be eliminated from the bucket every minute. So if you put 100 marbles in the bucket, you walk away for a minute and you come back later, 12% of those marbles will exit the bucket and be lying on the floor, right? Now there's 2 other processes. K12 has a rate constant of 0.11 minute to the negative 1. Another way of saying that is 11% of the number of marbles in V1 are going to leave V1 and end up in V2. So once again, you put 100 marbles in the bucket, you walk away for a minute, and then you come back. 12 marbles will have fallen out onto the floor, and 11 marbles will have moved next door into the V2 bucket, which is a bucket that's about twice as big. The rate constant for K13 is about 0.04 minutes to the negative 1, which means 4% of what's in V1 will go to V3. So if you're trying to figure out how many marbles you need to put back into the bucket to keep it at 100, you just have to know the sum of those 3 rate constants, okay? So K10 is about 12%, K12 is about 11%, K13 is about 4%. You add them up, it's 27%. Or in other words, 27% of the marbles in V1 will exit V1 at the end of the first minute, which means if you want to administer marbles, you need to administer 27 marbles per minute for the first minute. Another way of saying that, to bring this back to the propofol concentration, is 27 milligrams needs to be administered in the first minute. So if you multiply 27, that's 2.7 mils of propofol. What's 2.7 mils per minute multiplied by 60 minutes, it ends up being about 150 mils per minute or thereabouts. And that's how the Simtiva and how your pump app actually figures out that the initial rate of administration has to be about 150 mils per minute. Now, I use the numbers to illustrate it, but it's not going to be exactly the same because it doesn't literally wait for a minute to do these calculations. It does these calculations multiple times every minute. So I'm using it as a simplified analogy to explain that. Does that make sense?
I think that's really clear. And the important thing is that, again, not to fixate on the numbers. What Anthony's trying to drive home the point is that if you go into the exam and say 27 mils will be leaving in this example, that's not what he's trying to explain here. He's trying to explain the concept that you're putting a drug into the V1 compartment and that bucket has multiple holes attached to it. And you need to keep filling that bucket to make sure that that central compartment stays the same as time does. And how do you figure that out is based on the rate constants, not what the numbers of the rate constants are for you to rote learn, but you know that the concepts are that there's these rate constants that are taking the drug away from that central bucket.
Yeah. Now, what happens in the second and third and every subsequent minute becomes even more complicated, okay? So the maximum rate at which the marbles are leaving the bucket is going to be in the very, very first minute, and it's simply going to be K10 plus K12 plus K13. That's the maximum rate at which the marbles are going to be leaving the bucket. So in the first minute, it's 27 marbles have left the bucket. There's 11 in V2, there's 4 in V3, and there's 12 lying on the floor. Now you've taken 27 marbles, you've popped them back in, so you now have 100 marbles in your V1 once again. Now, what happens if you walk away for a minute and then come back? What's going to happen? Well, every minute, 27 marbles are still going to leave V1. 12 will fall on the floor, 11 will go to V2, and 4 will go to V3. But in addition to those distribution and elimination rate constants, you also have to factor in the redistribution of marbles from V2 and V3 back into V1. So at the start of the second minute, we said before, there are 11 marbles in V2. So what you have to calculate, in addition to the 11 marbles going from V1 to V2, you have to calculate how many marbles come back from V2 to V1. To do that, you need to know the rate constant for redistribution, or K21. So the intercompartmental clearance from K21 back from V2 back to V1 is governed by the rate constant K21. So K21 happens to be about half of K12, or 5.5%. So you have to factor in that 5.5% of the 11 marbles in V2 go back to V1. Now, I'm not sure what 5.5% of 11 marbles is. It's about 0.6 of a marble or something like that. So the net transfer of marbles from V1 to V2 in the first minute is 11. The net transfer of marbles from V1 to V2 in the second minute is going to be 11 minus 0.6, or in other words, 10.4. Now, the same thing happens for V3, but V3, there's only 4 marbles in there to start with, and the rate constant for redistribution, K31, is extremely slow. It's 0.3%. So what's 0.3% of 4 marbles? It's like 0.01 of a marble, something like that. So the answer to the question of what happens if you walk away at the end of the first minute and come back at the end of the second minute, there is still 27 milligrams leaving V1, but there is 6.01 milligrams coming back to V1. So the concentration in V1 would not be 73 divided by 20 litres. It would be 73.61 divided by 20 litres, which means you do not need to top it up with 27 milligrams of propofol. You only need to top it up with 26.39 milligrams of propofol, right? It's slightly less. And that's the reason why the propofol administration would no longer be 150 mils per minute. It'll be down to about 147 or 146 mils per minute. And so as you progress into the third, the fourth, the fifth, the sixth minute, you can manually do these calculations yourself on an Excel spreadsheet. And this is something that I do with my trainees. If we have a very long case that's several hours and we're running Propofol TCI, I will actually get them to do these calculations and predict what the rate of administration at the 1 hour mark is going to be. And then at 1 hour, we compare and see how close we are. So it's hard to do, but for a computer microchip, it's very easy to do. And the way that it does it is by equation number 5. So why don't we go back to equation number 5, and we'll just show you the actual equation for how the computer calculates the mils per minute. Now we think of concentrations, but you can see how if you just multiply the concentration by the V1, you end up with the bolus dose. So all that's really relevant is the bolus dose. You started off with a bolus dose of 100 milligrams, and then a certain percentage of that 100 milligrams has left V1. And you want to figure out how many milligrams do I have to top V1 up with in order to get it back up to 100. So remember before I said the rate of administration in milligrams per minute is equal to your initial bolus dose, 100 milligrams, multiplied by, open brackets, a whole bunch of complicated maths, close brackets, right? And what's inside that closed brackets is just a number for K. Now, the maximum number for K is the initial infusion rate, which is simply K10 plus K12 plus K13. Over time, as V2 and V3 equilibrate, the net transfer of marbles from V1 to V2 is going to be equal to the transfer of marbles from V1 to V2 is going to be the same as the transfer of marbles from V2 to V1. So that distribution and redistribution cancels each other out, does not contribute to the calculation. Eventually, with enough time, the same thing happens with the slowly equilibrating compartment. So at time infinity, the rate of administration is simply equal to the bolus dose in milligrams multiplied by your K10, which is the rate constant for elimination. And the actual equation is, that's what's inside the actual brackets is K12 times e to the negative K21t plus K13 times e to the negative K31t plus K10. So K10 is the only one that does not decrease with time. Both the first and the second of those rate constants will decrease with time, because when time is 0, anything raised to the power of 0 is 1. So the initial rate is K12 plus K13 plus K10. And then as time progresses, as t increases, you are multiplying your K12 and your K13 by an increasingly negative number. So it's going to start at K12, and then it's going to eventually go down to 0. K12 will approach 0 first, then K13, and then eventually you're just replacing the losses from elimination. And that is how that calculation works. And so if you want to figure out...
super daunting to look at initially.
Yes, but if you understand what the equation is doing, you understand that it's simply whatever is inside that brackets at time 0 in the Marsh model starts at 0.27. And then at time infinity, it ends up being 0.12. So what's inside there is just a number which is somewhere between 0.27 and 0.12. And the mathematics calculates what that number is. But at the end of the day, it's still simple. It's still a bolus. It's still 100 milligrams multiplied by a number. So it's 100 milligrams multiplied by 27 in our initial example. You put 27 marbles back in. Eventually, it's the 100 milligrams multiplied by 12% or 0.12. You end up administering 12 marbles. And in between, the computer will calculate the rate at which the marbles are leaving V1. And this is why, if you just leave your Propofol TCI Marsh model running indefinitely, it will eventually end up being 100 milligrams multiplied by 0.12, which is about, 12 milligrams per minute.
Yeah. And
so you multiply 12 milligrams per minute by 60 minutes, it'll be about 70 or 80 mils per hour. So we can go back to our SimTimer app and see what's it going to be running at in sort of 4 or 5 hours time. And it's going to be around about 70 or 80 mils per hour. I don't know exactly what it is, but it's just simply replacing the losses from elimination.
And if you look at text, that usually V1, V2, and V3 usually at 20 hours have reached that state where now the amount of drug you need to put in is equal to K10 plus your maintenance or whatever you're doing.
Yeah. If you scroll up, Arnie, you'll see what has happened. So here we see a bolus of 100 milligrams was given, and then an initial bolus of 150 mils per hour was given for about 8 minutes, and then it dropped down to 135 mils per hour, and then it dropped down to 112 mils per hour, and then it eventually ends up after 5 hours going at 80 mils an hour. And so that should not be a surprise if you understand the mathematics behind it. The incorrect thing to do is to rote learn that all Propofol TCI eventually ends up at 80 mils an hour. That is not the point of this. The point of this is to understand that eventually the the equation will simply be replacing the losses by elimination. So the rate constant is going to be K10 plus K12 plus K13 at the very start, and then K10 solely at the very end, and it's going to decrease in a, is going to decrease because both of those are negative exponential washout functions with time. And that's what the Propofol Marsh model does. The beauty of it is that it's simple, but it does have some downsides because if the rate constants do not change with age, you could end up, for example, we've got an 88 kilo 20-year-old. What happens if you have an 88 kilo 80-year-old? Well, if you're using the Marsh model with exactly the same weight and you're targeting a plasma concentration of 5, it will give exactly the same bolus dose and administer the exact same mils per hour. So that's a big deficiency in the Marsh model. It'll underdose young people, it'll overdose old people. If you've got someone who's about 50 or 60, it'll maybe get the dose about right. And the other thing, which is a problem, is if you've got someone who's very obese and they weigh 120 kilos, that is very different to someone who is, a bodybuilder, tall, muscly kind of athlete who weighs 120 kilos. Those are not going to be the same body composition. So those are the limitations of Propofol Marsh model. And the other thing is, it was designed for plasma targeting. So yes, you can retrofit it with a KE0 to target your effect site. But if you are going to target the effect site, it kind of makes sense to use the Schneider or Schneider model. Schneider is the correct pronunciation. I say Schneider because I like to deliberately mispronounce it because everybody else does. But it doesn't matter which way you pronounce it. The Schneider or Schneider model is the best one to use for effect site targeting, which probably brings us on to the 6th equation.
Yeah.
And we might as well go through that now.
And just to add on to what Anthony said, a term that you should know when we're talking about TCI model, which is important, is that these changes in fusions lead us to call a TCI model a variable rate infusion. And that's where it comes from. It's a variable rate because of what's happening in K2 and K3 with time as the infusion continues. It's not a fixed rate infusion, and that's really important to know. It's not like setting up a pump and just putting it on 20 mils an hour. The TCI model, because of these algorithms and the 3-compartmental model, changes its infusion, and that's called a variable rate infusion.
Yeah, and the SimTiva is also variable rate, but it doesn't change it every microsecond, because the whole point of SimTiva, that website, is if you don't have something, you can't be changing it every 3 or 4 seconds. So it says it's an approximation. Run it at this rate for 8 minutes, then decrease it to that rate, etc. Okay, so the final of the 6 equations is the equation that tells you plasma concentration is easy to understand. We can measure it. We can't measure it in practice, but it is possible to measure it in a laboratory research setting. Effect site concentration cannot be measured. Effect site concentration is inferred, and it is based on the following logic. If you plug someone into a BIS monitor and you have not given any propofol, the BIS is going to read, roughly 100 or thereabouts. If you give them a bolus dose of propofol, the BIS will stay at 100, and then it'll start to go down. It'll reach a nadir, which is the lowest number it gets to, and then it'll slowly come back up again. Now, what we're inferring is that the BIS going down and up is roughly equivalent to the concentration in the effect site going up and then down. How quickly the effect site goes up or down, governed by the rate constant for equilibration, or KE0. People call it KEO, KE0, KE0. It's actually doesn't matter what you call it, because a lot of people get confused by this concept. Now, the best way to think about the KE0 is to think about as a rate constant of equilibration between plasma concentration and effect site concentration. So the dCE dt, in other words, the change in effect site concentration as a function of time, is going to be equal to your KE0, which is your rate constant for equilibration, multiplied by, open brackets, the difference between your plasma and effect site concentrations, close brackets. Okay, so at the very, very start, let's say you give a propofol bolus and your plasma concentration goes up to 5, your effect site concentration starts at 0. Well, the effect site concentration will start to approach your plasma concentration very quickly. And then as time progresses after your bolus, let's say you're just given a bolus and you're not doing an infusion, the plasma concentration will start to wash out and the effect site concentration will start to go up. So the rate of change of effect site concentration versus time is going to decrease. And then eventually you get to a point where the plasma concentration has dropped from, let's say, 5 down to a lower number. Your effect site concentration has increased from 0 up to a higher number. And you'll eventually get to a point where your plasma concentration equals your effect site concentration. That is the time to peak effect, and that is when the BIS is at its lowest. Okay, it's the only time you actually know what the effect site concentration is, because if you know that the time to peak effect is, let's say, for example, 1.6 minutes, and you take a plasma concentration sample of blood at 1.6 minutes, you know by definition or by logical extension, the plasma concentration has to equal your effect site concentration. After the time to peak effect, the plasma concentration will continue to decrease, and then that sets up the reverse concentration gradient. So your rate of change, dCE dt, is going to start to become negative. Or in other words, your effect site concentration will have already peaked, and now it is going to decrease. It's going to follow your plasma concentration curve. So that concept of having a time to peak effect and having a effect site concentration that approaches the plasma concentration, and the rate at which it approaches is governed by the rate constant for equilibration, are the key things that you need to understand if you're going to start targeting the effect site concentration with a Schneider model.
And so then we can talk about the Schneider model and plug in the examples to then SimTiva as well.
Yeah, well, why don't we go back to SimTiva, and why don't we just ask the Schneider model or the Schneider model to do exactly the same thing. So we've got a 20-year-old. We'll keep them at 20. We'll say that they're 88 kilograms, just because that's what it was in the first place. Let's say they're 188 centimeters tall, which means they're about BMI 25. Let's keep them male, and let's go Propofol Schneider. Now, you don't want to target the plasma concentration. You pretty much always, if you're inducing anesthesia, you always want to be targeting the effect site concentration with the Schneider. So let's proceed, and let's see effect site targeting. Let's do 5 again.
Yeah.
And let's see what the pump ends up doing.
We start that. So here what we're saying when we're doing effect site targeting is that the time to equilibration is equivalent to the time to peak effect with effect site modeling.
Yeah. So what we've done then is we have artificially created this example, because if you're doing this at home, you will see that the Propofol pump is going to give exactly the same bolus, 100 milligrams. The difference is it gives the 100 milligrams and then it pauses for a variable amount of time, and then it starts an infusion, usually at a lower rate. So what's actually happening? How is the pump actually targeting the effect site? Now, the easiest way to think about it, if you scroll down to the model parameters are kind of all over the shop. They are completely different to the Marsh model parameters. Notably, the volume and distribution of the central compartment is very, very low. It was 20 litres for this patient in Marsh. It is now 4.27 litres in Schneider, and it does not change at all. So what's actually happening is you're targeting not the initial plasma concentration, you're targeting what you want the plasma concentration to be at the time to peak effect, right? Targeting an effect site peak of 5 is the same as saying, when the peak effect is happening, I want the plasma concentration to be 5. Because as you can see on the SimTiva, the plasma line goes way up, and then it starts to decay, and then your effect site concentration starts to approach. And then once both of them meet at 5, then the pump starts giving a variable rate infusion, and it tries to maintain the dose in V1. It tries to maintain the number of marbles in the bucket in the exact same way as that we just described in the previous model. But because the rate constants are different, and because the V1 is different, you're going to get a different rate of administration. So in Marsh versus Schneider, for this patient, they both get a 100 milligram bolus, but the difference is Schneider waits for 1.6 minutes or thereabouts, and then it starts giving the infusion bolus at a lower rate. Now, this is the tricky part. If you look at the pump is going to say 5, but it doesn't matter what's on the pump. What matters is how many milligrams you gave as a bolus and how many mils per hour you are giving as an infusion. The number on the pump is a means to an end. The end is the bolus followed by the infusion. Changing, and we should not lose sight of the fact that the number is not the primary thing you're trying to control. You're trying to control the mils per hour that you're giving.
On this graph, you can actually see what Anthony is talking about. This is the time to peak effect, 1.21, where your CP and your CE are essentially the same, which is referred to as the time to peak effect. And then from there, you can see there's this ongoing variable infusion rate, which is trying to maintain that at 5 in this Simtiva app, which is really nicely illustrated. Unfortunately, one of the downsides of the audio podcast, but if you're doing the Simtiva app, you can see this illustration if you prefer to learn on a visual kind of aspect.
Yeah, we mentioned before that if you're doing a Marsh model and you double the input weight, it'll simply double propofol bolus dose and then double the maintenance infusion rate. Now, Schneider does have a fixed V1, which is very small, but one of the advantages is that it does alter some of the rate constants based on your inputs. And you recognize this when you're inputting your stuff, that it asks for things like age, height, weight, and sex. So let's think of two hypothetical patients. We've already done a 20-year-old who's 88 kilos, 188 centimeters tall. Let's say we take the exact same person and let's make them 80 years old. Let's make them the same weight, 88 kilograms, the same height, 188 centimeters. Let's keep them as male. Let's make them Schneider, and let's target an effect site concentration of 5 again. And let's just see how a 20-year-old versus an 80-year-old, because in Marsh, they'll be exactly the same because the weight is exactly the same. Let's plug it into Simtiva and let's describe what you see, Arnie.
So what we see is initially, the first thing you should pick up is that the bolus dose is lower than the patient who was 20 years old. And it's roughly 20% lower. And that's because the Schneider model, Schneider, now you make me want to say it in different ways, is using...
Fun to deliberately mispronounce it. That's right.
using the different parameters. So it's using age, it's using weight, it's using lean body mass, and it's adjusting for gender to calculate this. So what you see is that the bolus is lower, but importantly, the variable infusion rates over the next 5 or 6 hours are also lower compared to our 20-year-old, 88 kilo, 188 centimeter, same BMI patient who's also male.
Yeah. Now let's pick this apart and figure out why that's the case. So if you're using the Marsh model, let's say you dial up whatever your input weight is into the Marsh model, and it says you're going to give a 100 milligram bolus. What would most people do if they've got an 80-year-old? And if they wanted to, they say, well, I want to give 20% less. You would then either decrease the target infusion, the target, or you could decrease the V1, right? If you decrease the weight by 20%, it will decrease V1 by 20%, and you will end up with a 20% lower bolus dose. That's how the Marsh plasma targeting model works. But if you look at the model parameters of this 80-year-old versus the last 20-year-old, you see that the VC is 4.27. The volume of distribution of the central compartment has not changed, right? And this is confusing because you're saying, well, hang on, Anthony, didn't you tell me that if you have a dose in milligrams and you divide it by a V1 of a volume of distribution, you end up with a concentration? So how can you have the same V1 of 4.27 litres, and how can you have the same target concentration of 5 but end up with 2 separate doses? And the answer to that riddle is you are not targeting in Marsh, you are targeting the initial plasma concentration, and that has a V1. In Schneider, you're targeting the plasma concentration at the time to peak effect. So the relevant volume of distribution is the volume of distribution at the time to peak effect. The VDPE is going to be a higher number than the VI. So VI is the smallest, initial volume of distribution. VDPE is bigger because, it just has to be the case, because if you give a bolus dose and then you come back and measure it 1.5 minutes later, some of that propofol will have left V1. So you're going to have a lower plasma concentration. So if you do the mathematics, VDPE always has to be higher than V initial. And if you keep running indefinitely, you end up with volume distribution at steady state, which is going to be a higher number still. This is the problem. You see why volume distribution can be very confusing if you are not specific about which volume distribution you are talking about. So let's go down to, let's compare the two
Constants.
parameters. Okay, so
Yeah.
you've got a 20-year-old versus an 80-year-old.
So I'll show you the 20-year-old first.
Yeah,
And
so let's look at the 20-year-old first.
so you can
The
say
one you want to keep an eye on, so K10 is 47%. Now, K10 does not change with age. It does change with height, weight, and sex, but K10 does not change with age. Therefore, when we look at the 80-year-old, we should also expect that it's 47%, exactly the same, right? Now, let's skip over K12. Let's go to K13. K13 in both is 19.5%. K13 never changes in the Schneider model. It will always be 19.5 for everyone, regardless of age, height, sex, weight. So let's just check that that's the case in both patients.
And it is.
Yep. 19.5. So the difference is the K12 in the young person is 48, 49%. Now, the way K12 is calculated, if you look at the actual textbooks and whatnot, it's K12 equals a number, and then you adjust that number based on age. So you can see in the 80-year-old, it's not 48%, it's 15%. So the rate constant, the thing that makes an 80-year-old different to a 20-year-old in the Schneider model is that there is a much slower rate constant for distribution from V1 to V2. In other words, you put the marbles into the bucket, the marbles will leave the bucket and fall on the floor at the same rate. They will transfer into the V3 bucket at the same rate, but they will transfer into the V2 bucket much, much slower, which means more marbles are in the bucket, which means if you're calculating the rate of infusion, you do not have to put as many marbles in. Now, here's the interesting part. I mentioned before that the time to peak effect is about 1.6 minutes. Now, it's not exactly 1.6 minutes for everybody in every single Schneider model. Sometimes you turn on the pump and it says, we're going to calculate the KE0 to make the time to peak effect 1.6 minutes. But the original one and the one that Syntiva uses, if you look closely, there is a different time to peak effect for the old person versus the young person. The old person has a time to peak effect of 1 minute 38 seconds, which is what, 98 seconds. And the young person is more like 1 minute 21, which is, what's that, 80 something seconds. Doesn't make much of a difference. Why you're bandering on about 10 seconds here and there. Well, I'm going to explain to you why it's a difference. Now, remember before we said that the initial rate at which the marbles leave the bucket is simply equal to K10 plus K12 plus K13. So let's go to the model parameter for the young person.
Which is here. Yep.
So if we go down to the model parameters rather than so in the young person, if you want to calculate the initial rate, it's 47% plus 48% plus 19.5% equals 116%, or 1.16 minutes to the -1. Now, that's a very high rate constant. So a better way to think about that is divided by 10. So what's 1 minute divided by 10? 6 seconds, right? So instead of thinking it's 1.16 rate constant, think of it as 0.116 for every 6 seconds. Or in other words, every 6 seconds, 11.6% of the marbles leave the bucket. So what you end up then saying is, I want to end up eventually at the time to peak effect, which is what, 90 seconds. So that's about 16 6-second periods, right? So at the time to peak effect, I want the plasma concentration to be 5. And if I want it to be 5, that means 6 seconds earlier, it has to be 11.6% higher than 5, doesn't it? So you can calculate that. And then you go 6 seconds earlier than that, it needs to be 5 times 1.116 times 1.116 again. It's kind of like compound interest. You start at the time to peak effect and you extrapolate backwards, going up by 11.6% every 6 seconds until you get back to time 0. And if you calculate that out, you could help me on the calculator if you like, or do this at home. Let's see if this works out. So I'm going to type into my calculator. Do you want to bring the calculator up on the screen, or just do it on your phone? We can do it on the phone.
The maths that Anthony's trying to say is you ended up at a time to peak effect of a concentration of 5 mics per mil. you know that every 6 seconds, 11% has been lost from that concentration. What was the concentration at the start? So you're reverse engineering to figure out what the bolus dose was at the
Yeah.
start, being time zero, to get this number. So if we
So let's
say,
start with 5 micrograms
yeah,
per mil, and you want to multiply that by 1.116. Okay, so that's just compound interest calculation. But you want to raise that 1.116 to the 16th power because there's 16 increments. Is that right? Or is it? No, it's probably more like 13, isn't it? This is 1 minute
oh yeah,
21.
because 120.
How many 6 seconds? It's about 13, isn't it? There's
Yeah.
13 6-second increments in 1.21 seconds. So the equation is 5 times 1.116 raised to the power of 13, or 13.5. It's about halfway. So close brackets, that equals 22.000. So what that means is if you extrapolate back, if you want the plasma concentration to have dropped to 5 at 81 seconds, you have to start with a plasma concentration of 22 initially. And if you're looking at the Centiver app, that red line, which represents plasma concentration in the Schneider model, goes from 0 up to 22, and then it has a negative exponential washout curve down to meet the other curve at 5. Now, 22 is the initial concentration. What happens if you multiply 22 milligrams per litre times by 4.27, which is the volume of distribution? You end up with about 95 milligrams, according to my calculation. So it's not exact because we're doing kind of rough ballpark back of the envelope calculations, but that is how you end up with a calculated bolus dose of, in my case, 95 milligrams. In the accurate proper thing of the Centiver world, it's 100 milligrams.
Yeah.
So that's just an illustration that you're not targeting the effect site, you're targeting what the plasma concentration is going to be at the time to peak effect, which is exactly the same thing. And once you've got a plasma concentration of 5, which equals the effect site concentration of 5, then it's simply a matter of replacing the marbles as they leave V1 in exactly the same way. Now, why don't we, just for fun, why don't we do the same thing for the
80-year-old.
80-year-old? So if you go down to the 80-year-old, let's have a look at their rate constants. So the rate constant is 47% plus 15% plus 19.5. So if I add them all up, I get 82%. Okay, so and the other thing is the time to peak effect is longer in this one. It's kind of closer to 16.
Yeah, 1 minute 38. So yeah, let's say
Okay.
16.
So there's
16
6-minute increments. Okay.
Yeah.
So what you want to do, the equation is 5 multiplied by 1.082 raised to the power of 16 or thereabouts. And that gives me a plasma concentration of 17.64. So in order for your plasma concentration in your 80-year-old to fall to 5 at the time to peak effect, you have to start with a plasma concentration of about 18 at time 0. So if you start at 18, and you multiply that by 4.27, you end up with what, 77 milligrams, according to my calculation.
Yeah, roughly.
So that's how the pump calculates the 80 milligram bolus. This is rough back of the envelope calculations for us to do, but it's very easy for a computer to do it. It doesn't have to wait a minute. It doesn't have to wait 6 seconds. It can do it multiple times per second. So what you get on the computer is going to be more accurate version of what we just did manually by hand. Now, that's how you get the different bolus dose. Now, what's the initial infusion rate in the 20-year-old versus, so we've had the infusion going for about 10 minutes now.
Yeah.
The 20-year-old is getting
99
mils per hour of propofol, and the 80-year-old is getting what? It'll be a little bit lower, won't it?
94.
94. So it's a little bit lower. And that's because the rate constant governing distribution from V1 to V2 is a lower number, slower in the 80-year-old. Now, when you fast forward a couple of hours, V2 is going to be equilibrated completely, but K13 is going to be exactly the same. So if you fast forward to like 4 or 5 hours,
yeah.
what's our 80-year-old going at in 4 or 5 hours? It's
so
about
5 hours,
68,
68 mils an hour is the 88-year-old.
What about the 20-year-old? It's also 70 mils an hour.
Yeah.
So once again, that should not be surprising, because the thing that is governing the rate at which you are putting marbles into the bucket is simply the K10, and to a lesser extent the K13. But both the K10 and the K13 are identical in these two patients because they weigh the same they're the same height, and they're the same sex. The Schneider model is good because if you put in old people versus young people, it will alter your bolus rate. But it is obviously an 80-year-old does not need as much propofol to keep them anaesthetized as a 20-year-old after 4 hours. So that's one of the limitations.
And
Okay,
that's a really important clinical thing to understand. If you're going to be saying, I use the Schneider model in a long case because I'm going to give less propofol in the long run in the infusion. At 4 or 5 hours, you're giving the same as if you were running the Marsh model. Yes, cumulatively, you would have decreased less because you've used less bolus and then less before you got to that equilibration phase where you're just using K10 and K31. But you just have to keep that in mind from a clinical context.
And also in practice, what most people do is they realize this and they have workarounds. Okay, so they decrease the rate or they decrease the they don't run it. You don't run it at 5 for the entire 10-hour case. You bump it down to 4 or 3 based on other things. Okay, well, why don't we do another example to show you how changes in body composition can affect things. So let's stick with the Schneider model. Let's stick with our 20-year-old. But rather than having them 88 kilograms, let's make them 188 kilograms. So this is taking their BMI of 25 and making it more like 53.
In the same height.
Now, you can't do this on an actual pump a lot of the time, but you can do it in Simtiva. And we're going to go through why. So it comes up with a warning here. Do you really want to use that input weight? Let's say yes, keep using the total body weight, and let's see what happens. And we're going to do effect site targeting, and we're going to do 5. So it's the same age, 20 years old. It's a man who's 188 centimeters tall. But the only difference is they're 188 kilos rather than 88 kilos. So do you want to describe what you see there, Arnie?
So here, what we see is that our bolus dose is higher compared to our male who was also 20 years old and only weighed 88 kilos. So roughly it's 150 milligrams of what we're giving this gentleman. So it's 150% more, or 50%
Yeah, so
more.
150 versus 100, that does make sense to some degree because there's more of them. So you definitely do increase your bolus dose when you have greater weight patient.
Then what you see is a substantial increase in our variable rate infusion compared to our 88 kilo 20-year-old male. And if we go down to the model parameters, we can...
But just to highlight that, it's infusing at something like 230 mils an hour as opposed to like 100 or 120 or whatever it was. So here's another little point. If you look down at your pump and your pump is giving 200 mils an hour, something's gone drastically wrong, okay? Unless you're anesthetizing an elephant, most of the time your pump needs to be going at about 100 mils an hour initially and then gradually going down to about 50 in the vast majority of kind of cases. Now, the key here is that when you look at the parameters, you see, let's compare the 20-year-old, well, they're both 20. Let's compare the 188 kilo person versus the 88. The volume and distribution of the central compartment, exactly the same, 4.27, never changes. The K12, exactly the same because the age is the same. What has changed, however, is the K10. So the K10 in the obese person is 1.38 minutes to the -1, whereas in the 88 kilo person, it was more like 0.49. Okay, so there's like a 2.5-fold increase in your K10. And the reason for that is in the same way as K12 is calculated by saying K12 is a number, and then if you're older, we take some numbers off. The way K10 is calculated is K10 equals a number. If you're taller than 177 centimeters, we'll add a little bit. If you weigh more than 77 kilos, we'll add a little bit. And then we will subtract something based on your lean body mass. That is how K10 is calculated. So this works very well for people who are normal weight and people who are slightly overweight. But once you get up to the extremes of obesity, it kind of breaks down. And the reason for that is the way lean body mass is calculated. This was determined back in the 90s, where there were probably some obese people around, but it probably wasn't as big a problem. So what the model is trying to do by using lean body mass is to estimate fat-free mass. Now, lean body mass, by the equation, the James equation, will estimate fat-free mass pretty closely up until you get to a BMI of about 30, 35. And then what happens is lean body mass will go up, it'll reach a peak, and then it'll go back down again. So if you have someone who's a BMI of 53, the way K10 gets calculated is K10 equals a number. They're taller than 177, so we'll add a little bit. They're way heavier than 188, we'll add a lot. And the lean body mass is extremely small, or maybe even negative. So you're either going to subtract a very small number, or you may even be subtracting a negative number, making it more positive. Long story short, you end up with a K10 or a rate constant of elimination, which is ridiculously high and unsafe in clinical practice. Now, K10 contributes a little bit to the bolus dose, but it becomes way more important during the maintenance phase. And that is the reason why when you use Schneider like this, you end up with very, very dangerously high mils per hour infusions of propofol. And that's why you can't do it on most pumps. Most pumps will not let you put in a BMI greater than 38 for women and 40 for men. So what you end up doing is having a workaround or bodging it up or inventing a weight, or and the most common weight to invent is either adjusted body weight, which is ideal body weight plus 40% of the difference between total and ideal, or just making up a number, or just putting it up to the highest BMI that you can go. So that's how body composition alters K10, and that's why you end up with extremes of obesity getting dangerously high infusion rates in the Schneider model.
Very, very important concept. And again, just goes back to fundamental understanding what's happening with the rate constants, and also then figuring out how is this being adjusted based on my models based on Marsh or Schneider.
So what do you do when you have an extremely obese person? Well, you either have to use the models and recognize these imperfections. You can use adjusted body weight. That works okay, but it's not great. You can also just use the manual 10-8-6 rule. So the problem there is when you're using the 10-8-6 rule, this is where you run, you give a bolus dose, and then you run 10 mils per hour for the first, 10 milligrams per kilograms per hour for the first 10 minutes. Then you bump it down to 8 for the next 10 minutes. Then you bump it down to 6 for the next 10 minutes. The trouble there is, we've done these calculations before. Yeah, the trouble there is you've got to use ideal body weight for the induction bolus, and then you've got to use adjusted body weight for the infusion. Now, you can't change the weight halfway through. So I don't want to talk about Eleveld too much today, except to say that it's a new model. It is mathematically very complex, but it is also exactly the same as the other models in terms of its fundamental scaffolding. There is a V1, there is a KE0 for time to peak effect to enable effect site targeting, and there is a whole bunch of complicated mathematics that determines the rate constants. The problem people get into, if you want to start using Eleveld and you don't actually understand it, we could probably go through one more example. Do you think, Arnie? Well, why don't we go through?
Yeah.
The final example will be, let's say you want to be smart and you want to use the Eleveld model. So let's say you've got your 20-year-old patient. They weigh 188 kilos. They're 188 centimeters tall. And rather than doing Schneider effect site, let's do Eleveld effect site. Because
And
you know
this
that
is
Eleveld is
just
more
important
accurate.
from the safety perspective, because we don't want people to be overdosing people if they incorrectly use the Eleveld model, and we'll explain why.
Yeah.
So
This is the problem. If you ask your pump to do something, it will just do what you asked it to do. Now, if you did not understand what it was that you are, just before you go further, make it 188 kilos.
Yeah.
The point I'm making, if you ask your pump to do something and you did not know what it was that you asked it to do, it will just blindly do what you ask it to do. Like, that's your fault for not understanding what you asked the pump to do. Okay, that's why this is important. So let's say you've got a 20-year-old male, obese, 53 BMI. Let's go effect site targeting, because you know that Eleveld is meant to be more accurate in obese people. And let's just put in 5, because that's what you put for Marsh, that's what you put for Schneider, and hit start. And what do you see in the Eleveld model when you're targeting an effect site of 5?
you see a scary bolus in a patient. So
Yep.
if you put this in and you do this on the Simtiva app, the bolus that this patient gets is 525 milligrams as an initial bolus.
Yeah.
That is,
And the mils per hour are also much higher than what you need.
yeah.
And The reason for this is Eleveld solves some problems, but it creates another problem. The problem is if you scroll down to the model parameters, it's a different model, so you can't compare model parameters. It's just comparing apples to fish. But if you look at the KE naught there, the KE naught is 0.11. It's a very low KE naught. Now, there is one more graph that I want to show you.
Yeah, I'll bring
And the
this one.
graph that I want to show you is, it's a graph, it's figure 16.19 from Miller's.
This one here.
And what you see is, because once again, like changing the KEO of the pump doesn't change what's happening in real practice in the patient, okay? What happens is it changes how your pump approximates what's happening in the patient. So let's say you give a plasma concentration bolus, the bolus dose goes up to a peak, and then you get a negative exponential washout curve, which is the black dotted line. Remember before we said that the KE naught describes the rate at which your effect site concentration approaches your plasma concentration. So if you have a KE naught of 0.8, which is the red line, it will approach the plasma concentration very, very quickly, and you will get a peak effect that is earlier, and you will get an effect site concentration that is higher. If you change the KE naught to 0.4 or to 0.2, what you end up with is an effect site peak that occurs later, and it is lower. So the thing about the Eleveld model is it uses a very low KE naught. So you don't need to put in 5 like you do for Marsh or Schneider. The reason why you put in 5 or sometimes 10 if you're targeting the plasma is you're compensating for a deficiency in the model. Okay, most people have a workaround where they start off at like 8 or something and then they come back down to 4. The Eleveld doesn't have that. So partially the reason why you never really need to go above 3 is partially because the KE naught is lower. But the second thing, if you flick on to the next slide, which is figure 23.33 from the 10th edition of Miller's, there's this concept of CE50. CE50 is the effect site concentration, which will reduce your BIS by 50%. It's kind of equivalent to MAC. What MAC is for volatile anesthesia, CE50 is for Propofol TCI. And if you have a look at this graph, what you see is age 40 on the right, the effect site concentration that will take your BIS down to 47 is about 3. As you go up to age 80, you can see the green line decreases to about 2. This is what we mean when we say old people are more sensitive to propofol. What we mean is there is something different about their physiology such that the amount of drug you need to give them to produce the same clinical effect is reduced. Now, if you go the other way and you go down to a 1-year-old, the CE50 is going to be upwards of close to 4. So younger people are less sensitive to propofol. So you have to bear in mind what the CE50 is and how old your patient is. And so for most people, you want to be somewhere in between sort of 2 and 3 on your effect site targeting for your Eleveld model. And sometimes if you've got a very, very young, robust kind of patient, you might go up to 3.5, but you never put in 5. Okay, so let's go back to Simtiva and let's put a more sensible parameter in for the Eleveld model. So we'll keep everything the same, put in the actual age of 20. We'll put in the actual weight of 188 kilograms. We'll put in the actual height of 188 centimeters. But let's just say we want to target the CE50 of 3. So let's put an initial effect site target of 3 rather than 5.
There you go.
So you do not have to make up different weight scalars. You put in the actual age, height, weight, sex, but don't use the same workarounds that you use for the other models. Just put in 3 and see what happens.
Here we are.
And what kind of bolus and infusion rate are we seeing there?
So now we get a more appropriate bolus. So the bolus is 315 milligrams, which might or might not still be a bit high, but it's more appropriate compared to the 525 we were giving with the CE of targeting 5 mics per mil. And we're getting a more appropriate variable infusion rate closer to the 100 down to the 70 mils an hour as time goes from time 0 to 4 hours. So you're seeing that it's more appropriate and it actually has adjusted for what we need to do. So you don't need that plasma overshoot that you get, or you don't get that plasma overshoot where you plug in the CE of 8 or 7 with the other models to try to get to that bolus range to get to the desired effect site as soon as possible.
Yeah, and if you scroll down to the model parameters, you can see that the model parameters have not changed. They're exactly the same when you do a TCI targeting a 3 versus a 5. It's just that you're using the model in the way the model is intended to be used. You're not using a workaround that you have gotten so used to with the other models that you kind of use it without even thinking. Now, this is not to say that Eleveld is better. That's not the point. I don't think Eleveld is better or worse. It's just a different model. So it is advantageous when you have extremes of age and extremes of weight, but the advantage is you don't have to make up a number for the weight, and you don't have to change your target concentration with your workarounds. You're not going to get necessarily better clinical outcomes, but it can stop you from doing a dangerous overdose or underdose of propofol. And if you look at what the makers of the Eleveld model, the thing that they claim is true. When you put in the actual body weight and age and height and sex, etc., it gives you bolus doses and infusion rates that more closely align with what you should be doing if you read, for example, the product information or the Society of Bariatric Anesthesia 1086 rule for Propofol TCI when you're not using TCI. That's really the only claim that they're making, and that claim is true. But if you've got a young, fit, healthy kind of person, it's not going to be that different to using a model that you're familiar with a workaround. The Eleveld model, if you want to boil it down into basic things, is it gives a higher bolus at the start and a lower infusion rate for a maintenance infusion. And you never really should be you should be thinking in terms of like a plasma concentration, an effect site concentration target of somewhere between 2 and 3.5, and kind of just hanging out there and adjusting to BIS. And that's probably all we really need to talk about. I don't bring it up because Eleveld is really important for the primary exam. I'm really just bringing it up to illustrate how changing the KE0 can change how well your model approximates real life. And therefore, if you don't understand what you're doing, you can give dangerously high or dangerously low levels of propofol. And it is your fault. If you ask the pump to do something that you don't understand and something goes wrong, don't blame the pump.
Yeah.
And the flip side of that is the
onus
more
is
you
on you.
understand about all of this, then the more safe your practice will be. And that is the entire point of learning this in a great amount of detail in the formative years of your anaesthetic training.
That was very, very good, very in-depth discussion about TCI modeling. And it's a thing that we do pretty much from, like, I've been doing anesthetics for 4.5 years. We started off with having in our TPS requiring 50 TIVA cases as a tick base. And pretty much I would argue that 60 to 70% of my cases are TIVA. And so using a TCI model in majority of patients, and if you don't understand how it works on the safety parameters, on what is the guidelines to make sure you're using it appropriately and adjusting it, because not every patient is that 20-year-old robust patient. The ones that we're worried about are the ones that are extremes of age with the physiological variables that have happened, hemodynamic shock, sepsis. Those are the ones where you need to be able to be very careful on how you're using not only the bolus, but what the variable infusion rate's doing. Because what you're trying to supplement is you're essentially trying to give a task to a machine so that you can focus on other things. But you need to be aware of what that machine is doing so that you're not jeopardizing the patient.
And it is important to realise that because Propofol TCI, there's no two ways around it. It is superior to volatiles during the maintenance phase in a lot of ways. Not every way. Like, I don't only use Propofol TCI by any stretch, but there are certainly people who exclusively use Propofol TCI because it does have a lot of advantages. But if you put a vaporizer on 2% SIBO, that's not going to malfunction unless your vaporizer runs out of SIBO and you don't replace it. There's a few things that can go wrong. There is far more moving parts in the Propofol TCI, and so there's far more ways that it can go wrong, from just like simple mechanical stuff like a cannula being tissued, right through to this patient does not have the physiology that warrants using that particular model. And so never lose sight of the fact that what your model is and what your number is a means to an end. It's a way of getting a bolus into the patient and a way of maintaining anesthesia by giving a rate of administration of propofol. And if you don't get too fixated on the number and you use it appropriately, it can be a very, very powerful tool. And it's certainly got way more popular over my career, and it's certainly got a lot of advantages from across a wide range of things. I'm not at the point where I exclusively use it, but I do like to use it. I think it's worth pointing out the downside of it. The downside about propofol is the patient does not stay still.
Yep.
So propofol will stop someone from being aware, but you always need to be using it with something else to stop them from moving. That something else can either be paralysis, or it could be intense opioid analgesia. So remifentanil infusion goes along hand in hand with propofol infusion a lot of the time, or regional anesthesia, so a spinal or an epidural or a plexus blockade, because the propofol in and of itself does not stop the patient from moving the same way as volatile anesthesia does. And so that's one of the drawbacks. And if you think that running your if you exclusively use volatile, then you move to propofol, you go through a period where you go, well, the patient's moving every time they operate, and it's because the propofol is not meant to be keeping them from moving. You've got to stop them from moving by giving either analgesia, regional anesthesia, or paralysis. And that's another way you can go wrong with propofol. Turning the propofol up so high that they stop moving means you're running it at like 150 mils an hour, which negates all of the benefit of using propofol.
Anthony, I think we might call it there, because I have taken more than an hour and a bit of your Saturday. But I want to thank you so much for volunteering your time and going through this. And I think the really important things that you have touched on are important concepts, not just for the primary teaching, but just general principles that every anaesthetist should know just to improve their safety of practice. And if you go back to the initial 4 slides, the first 4 slides, where we go through those equations, the concentration graph, the 3-compartment modeling, those, if you know those well and understand it, not just rote learn it, you will do well in the exam, but also do well in your clinical practice.
I think so, yeah. Well, thanks for having me, Arnie. And I look forward to next time we're in the same theatre, and I'll go through. Hopefully, we get a 10-hour case where I can get you to calculate all of those.
I'll be manually calculating.
Really look forward to
that. Thanks, Anthony.
All right. See ya.
People try to throw it shade, brainwashed by the climate brigade. I'm not trying to diss those who use TiVo, but I prefer SIBO anesthesia. I give SIBO anesthesia, baby. Needlephobic child with a mediastinal mass. Like to see you try that without gas. Turn up the nitrous cause you know it's good. I still use halothane if I could. I'll give SIBO anesthesia, baby. Don't give a damn about Marsh or Schneider. I don't care how you pronounce it either. I've been around since the good old days, and I ain't gonna change my ways. I just give SIBO anesthesia, baby. I'm not real popular in recovery. I can't bring down a raised ICP. All my epileptics, they get more seizures, and they always bleed more in my GA seasons. I give SIBO anesthesia, baby. Wow, SIBO anesthesia, that's all I need. I don't need any of that Propofol TCI. As long as I get my red page Tuesday, actually, now that I think about it, maybe I should learn how to use Propofol TCI. It's probably better.